So now that we know something about writing out chemical reactions, identifying reactants and products, and balancing a chemical reaction, I'd like to talk a little bit about classifying chemical reactions under broad categories. These are not exhaustive lists of the categories of chemical reactions, but they're the most common for us and the ones that we ought to be familiar with right now. Generally, we can classify reactions as redox reactions or non-redox reactions, and we'll talk a little bit later in the next video about what redox means. By and large, decomposition, combination, single displacement, and combustion reactions are often examples of redox reactions. Again, it's not important that we know what that means right now because we'll talk about it in a little bit. Instead, what we're going to do here is describe how to identify each of these types of reactions. A decomposition reaction is one in which a single reactant decomposes or transforms into two or more products. A general formula for a decomposition reaction looks like this. Any old reactant, A, chemically transforms into two or more new products, perhaps B and C. The reverse of this process is a combination reaction, where two or more reactants get together to form a single product. In a combination reaction, a generic reaction might look like this. Two reactants, say A plus B, get together to form a singular product, maybe C. In a single displacement reaction, atoms of a single element swap places with an ion in a compound. In a single displacement reaction, we have one standalone substance take the place of a substance that's already in a compound. Perhaps standalone substance, any old atom, A, reacts with a compound formed from two or more elements chemically bonded together to take the place of one of the components of that compound. Perhaps A takes B's place in the compound and displaces element B so that it is all by itself as a product. A combustion reaction is the most specific type of reaction that we'll talk about here. For our purposes, combustion is the reaction of a carbon and hydrogen containing compound, something that contains explicitly carbon in some amount, hydrogen in some amount, reacting with molecular oxygen, O2, to form the specific products carbon dioxide and water vapor. So, unlike the rest of the examples of reactions so far, combustion is the only one where we have to look for specific reactants and products. It's not a generalized reaction so much as it is a specific type of reaction of a carbon and hydrogen containing compound. A hydrocarbon reacts with oxygen to form carbon dioxide and water. Lastly, in a double displacement reaction, we have a similar mechanism to the single displacement we saw above, except that in this case, two things will swap. These are sometimes called metathesis reactions. In a double displacement reaction, two partners come to a dance, say partners A and B, and C and D. And A doesn't really like its partner B, vice versa. C doesn't really like its partner D, vice versa. But ions A and D really would like to get together. And ions B and C really would like to get together. These compounds swap partners so that the cation of compound number 1 meets up with the anion of compound number 2. And vice versa. The next 5 slides walk you through specific examples of each one of these types of classifications of chemical reactions. So I will let you peruse them at your leisure, and we'll skip ahead 6 slides from now. So before we move on to talking about redox reactions, we're going to first explicitly discuss double displacement reactions. Double displacement reactions often take place when we mix 2 solutions together, each one containing a particular ionic compound dissolved in water. Of these double displacement reactions, there are 3 cases which could lead to evidence of a reaction. These 3 subcategories of double displacement reactions occur when, after mixing solutions together, a solid material forms. We call a solid material a precipitate, and solids forming by mixing aqueous solutions together are examples of precipitation reactions, which are double displacement reactions that form a solid. Alternatively, or in addition, when 2 aqueous solutions are mixed together, a gas might form. A gas-forming reaction is an example of a double displacement reaction. Lastly, when we mix things like acids and bases together to undergo neutralization, this is a double displacement reaction wherein water is formed, and evidence of reaction is given in terms of heat released. We're going to investigate each one of these 3 cases step by step. So the first category that we will investigate under the double displacement reactions, which again occur in solutions when we mix compounds like A and B plus C and D to have them swap partners to make products, say, AD and BC, are precipitation reactions. What we're going to do is label substances with their corresponding phases. In a double displacement reaction, compounds AB and CD are mixed with water in the aqueous phase. Therefore, they exist as ions floating around in solution. Ions can repartner with other substances to form things that may be themselves soluble or could be insoluble. S in phase designation indicates a solid. We're going to have to learn to identify when an ionic compound will dissolve versus when it will form a precipitate that stays solid in solution. In order to do this, we need solubility rules. In your PowerPoint slides on your Moodle page, this is a live link to solubility rules. I've posted a PDF copy of solubility rules on your course Moodle page, and I'll show you that PDF next. These are solubility rules. I will provide these to you for exam purposes for the rest of the semester. These solubility rules work in a hierarchical order, meaning the things that are topmost on this list apply universally and trump things that are below them on this list. For one thing, anytime an ionic compound is produced from ammonium or group 1A or alkali metal, those ionic compounds must always be soluble. Secondly, generally speaking, all chlorides, bromides, or iodides in ionic compounds render an ionic compound soluble, meaning capable of dissolving in water to make an aqueous phase, except when these halogens are with silver, mercury, or lead, which render a substance insoluble. Soluble means we'll label a substance with the aqueous phase. Insoluble means that we'll label a substance solid. Item number 3 says that chlorates, nitrates, and acetates always make soluble ionic compounds, and I'll let you read down the rest of this list to investigate further. We'll refer back to this list as we move through the next few slides. we're going to write out chemical reactions, and in addition to predicting the nature of substances in our reactants and products as soluble or insoluble, we'll write correct chemical formulas and balance reactions. So, let's do some practice with this. We're going to mix together solutions of various identities to produce products of particular forms. We are going to write out the results of each one of these reactions, giving proper chemical formulas, balanced chemical reactions, and appropriate phases as necessary. In reaction number 1, where sodium chloride, which we're told is aqueous, it must be aqueous because this contains a group 1A alkali metal, sodium, and is therefore soluble, reacts with silver nitrate, AgNO3, which is also soluble because it contains nitrate. According to rule number 3, nitrates are soluble. Produces sodium nitrate, whose chemical formula must come from Na+, NO3-, NaNO3. We just need one of each to make a balanced charge ionic compound. And silver chloride. Silver is Ag+, chloride Cl-. Again, just one of each is necessary to render a chemical formula with balanced ionic charges. So, first steps first, write out chemical formulas for our products. Secondly, balance this reaction. We see that we have one sodium on each side, one chlorine on each side, one silver, and one cluster of nitrate. So this is a balanced reaction as it stands. The last thing that we're going to need to do is identify the phases for our substances. Sodium nitrate must be soluble because according to group 1 of our solubility rules, sodium, an alkali earth metal in group 1A of the periodic table, must be soluble. According to rule number 2, chlorides are soluble unless they're in chemical compounds with silver, mercury, or lead. In this substance, silver is present with chloride. We say that when chloride is in a compound with silver, it is insoluble. It must form a precipitate. So we will label this substance solid. For reaction number 2, barium chloride reacts with sulfuric acid, H2SO4, both of which are soluble in solution, to produce barium sulfate and hydrochloric acid. Barium sulfate must have a chemical formula that comes from barium with a 2+ charge and sulfate with a 2- charge. Barium sulfate just needs one barium for every one sulfate. Hydrochloric acid starts with the name hydro, so we know that the anion must not contain oxygen. It must just be chloride. All acids have the cation H+. The correct formula for hydrochloric acid is HCl. Acids we can expect to be aqueous, and what's more is that HCl contains chloride, not with silver, mercury, or lead, so we expect this substance to be soluble in the aqueous phase. Barium sulfate, on the other hand, contains sulfate, which is insoluble with barium. This according to rule number 4 of our solubility rules. Barium sulfate is insoluble, which means that it is solid or precipitate in solution. We need to balance this chemical reaction to finalize things. So we'll notice that we have 2 chlorines in barium chloride, just 1 chlorine on the right-hand side. We need 2 HCl's. We'll notice that we have 2 H's by virtue of placing a coefficient of 2 here, 2 H's on the left-hand side. 1 barium on both sides, one cluster of SO4 on both sides, so we are balanced. That's the end of reaction 2. Take a few moments to see if you can write down balanced chemical reactions that show the correct formulas and phases for the next 3 reactions. Pause this video for a few seconds and then I'll come back and show you the results. Here's the balanced chemical reaction for number 3. Here's the balanced reaction for number 4. Keep in mind that mercury 1 is one of the polyatomic ions. It's got 2 mercury atoms with a total charge of 2+. And lastly, here's the final reaction, sodium hydroxide reacting with iron 3 chloride. Again, remember that when we write multiples of polyatomic ions in chemical formulas, we'll place them in parentheses. If we don't need multiples of them, we don't have to place them in parentheses. A second subcategory of double displacement reactions occur from gas-forming products, so-called unstable products, shown in these bullet points here. If ever we see the products H2CO3, H2SO3, or NH4OH, we'll replace them immediately with water and a gas. So in addition to looking at our solubility rules, we'll also be needing to keep an eye on these potential products: carbonic acid, sulfurous acid, and ammonium hydroxide. In the reaction between sulfuric acid and magnesium carbonate to make magnesium sulfate and carbonic acid, we form one of those key substances. We're also going to need to keep in mind the fact that we need to check for precipitates using solubility rules, in addition to keeping an eye on these gas-forming unstable products. Sulfuric acid must contain oxygen. We'll use adic-itis to help us identify which substance it is that contains oxygen. In this case, change the ending ic to ate. Sulfate must produce the anion for sulfuric acid. Acids always have H+ in their chemical formula. In magnesium carbonate, our cation is magnesium 2+. Carbonate is the polyatomic anion CO3 2-. Magnesium sulfate, again, has the cation Mg2+, anion sulfate SO4 2-. Carbonic acid, again, because it doesn't start with hydro, must be an oxygen-containing acid. Carbonate, again using adic-itis, comes from the CO3 2-, and acids always contain H+. This reaction can be written as follows. Sulfuric acid must be H2SO4. We need 2 H's for every sulfate. Acids are in the aqueous phase. Magnesium carbonate just needs 1 magnesium for every 1 carbonate. Carbonates are insoluble in water, but soluble in acid, so we should still expect a reaction. This reaction will produce magnesium sulfate, MgSO4, which itself is soluble, according to rule number 4 of your solubility rules, and carbonic acid, which must have the form H2CO3. It's an acid, so it's ostensibly soluble. But what we'll recognize is that H2CO3 in the aqueous phase is one of 3 usual suspects. As soon as we see it, we're going to cross it out and replace it with 2 new substances, water and a gas. H2O, which is liquid, L, and whatever's left over, a carbon and 2 more oxygens, CO2, which is a gas, G. The real products of this reaction are magnesium sulfate, water, and carbon dioxide gas. To balance this reaction, we'll recognize that we've got 1 sulfate cluster on both sides, 1 magnesium on both sides, 2 hydrogens, a carbon, 3 oxygens here, but 1, 2, 3 oxygens in substances that are not sulfate. So we are balanced. This is the chemical reaction that proceeds when we mix sulfuric acid with magnesium carbonate. A final subcategory of double displacement reactions occurs when acids and bases are mixed. An acid is a substance that ostensibly has H plus cations in its chemical formula and will generate a pH less than 7 in solution. Bases are substances that can give up hydroxide ions in solution and generate solutions whose pHs are greater than 7. We say that neutral water has a pH right at 7. Mixing acids and bases causes the reversion back to neutral water with pH 7 and is therefore an example of a neutralization reaction. Neutralization reactions always mix an acid and a base to form salt and water. In the example shown here, sodium hydroxide is a base, hydrochloric acid is an acid, like its name suggests, sodium chloride is a salt, an ionic compound, and water is water. The chemical formulas for these substances can be written by identifying cations and anions once again. Sodium is a +1 cation, hydroxide, OH-. Hydrochloric acid has the prefix hydro, therefore must not contain oxygen. H+ is always the cation in an acid. The anion must be Cl-. Let's write our chemical formula here. Sodium hydroxide, NaOH, which must be aqueous according to our solubility rules, reacts with hydrochloric acid, which is aqueous because it's an acid, to form sodium chloride, which is soluble, again according to our solubility rules, is not unstable according to our gas-forming products, and therefore stays intact just like it is, plus water. Every time we see water in a chemical reaction, we'll label it with liquid phase for these double displacement reactions. There is a worksheet on your course Moodle page entitled Predicting Chemical Reactions, and there is a solutions guide to that worksheet as well. I would encourage you to work your way through all of those problems, and we can talk about them when we meet next. Next up, we will discuss redox reactions in a separate video.